Good morning, everyone. And first of all, thanks a lot to Olga for inviting me to this conference. This is my first edition of the conference, and hopefully this will be the first of many. And thanks a lot for the introduction as well. So Ajith Parlikad, I'm based at the Department of Engineering at the University of Cambridge, and within the department, I'm based at the Institute for Manufacturing. So today, my talk is split into these three parts. I'll provide a very, very brief introduction to what we do in our research group, but also an introduction to the idea of asset management, because those ideas kind of link through to the rest of the talk. I'll then dive into what my understanding of digital twins are and some of the work that we do in this area. And towards the end of my talk, I'll also talk about some of the work we do, stretching the boundaries about the idea of digital twins. So hopefully this will be an interesting session for you. So my research group at Cambridge, I'm the lead for asset management at Cambridge. The goal of my research group is to really look at industrial systems and try and understand how we can improve the resilience of industrial systems through exploitation of data. So a lot of the things that you heard yesterday about predictive maintenance, about data analytics, AI, and so on, is very much part of the research that I do. The three key research questions that drive our research, you can see this. I'm interested in really using data to understand how we can model the behavior of industrial systems, especially complex industrial systems and networks. What kind of algorithms are required for us to effectively detect and predict disruptions in performance? So again, the stuff that you heard yesterday, anomaly detection, failure prediction, prognostics, and so on. But all of that really leads to that final question. What kind of decision frameworks, what kind of algorithms, what kind of techniques do we need to use to drive decisions that are appropriate for delivering resilient systems? So all of these things, technologies that we use, ultimately should be used to support decision making. We work with a lot of different companies across different industrial sectors, both from infrastructure as well as manufacturing and engineered systems as well. And our research is funded by the UK government. We've got some funding from Horizon as well. And we've got some funding directly from industries as well. So moving on to the talk, what is asset management? So you can read the definitions. I don't want to read it again. So I put a couple of definitions of what asset management means. One from the BSI PAS 55, which kind of can be seen as the origins of asset management, but also one from the ISO 55000 as well. The key terms in these definitions are, and I find the PAS 55 definition more useful to really understand the scope of asset management. It is about optimizing your decisions in a sustainable manner throughout the life cycle of the asset. So it's not just looking at one particular decision at one phase of the life cycle, it's throughout the whole life cycle of the asset. And most importantly, all decisions you make about your assets, about the organization, should align with that organizational strategic plan. So anything you do with your assets have to be organized. Now, that kind of is summarized by the simplistic definition, which talks about the coordinated activity of an organization to realize value from assets. Yeah. And nowhere you can see in this definition, it talks about maintenance, really. It's all about whole life management of assets. So just to pick this apart, what does actually all this mean? So asset management is about value-driven decision-making. So you saw that term value in the previous slide. And what we mean by value is that the three things coming together, the costs that you incur or the expenditure that you incur in managing and supporting your assets, the risks that you take by not taking certain decisions at a certain time, or risks that you take by making certain decisions as well, and ultimately the performance of the asset. So these three things, cost, risk, and performance, that come together to define what we see as value. The second thing is, second item here is quite important. Asset management really is a system-wide concept. Although you will be doing things to specific assets, so you will be maintaining a particular asset, a particular machine tool in a factory, or maintaining a bridge and so on. So the activities are done organized around specific assets. The value that you gain is from the whole system. So you can maintain a bridge, but the bridge alone will not deliver any value, right? It's the entire road network that delivers value. If the road that is connecting the network to the bridge is not maintained well, the bridge is not really going to deliver much value. A machine tool by itself is not going to deliver value if the production line is not organized properly. So when you're making decisions about the assets, when you're analyzing these assets, it's always good to think about the whole system and think about making decisions that are system optimal rather than just asset optimal. The third point is quite clear: whole life. When you make decisions about purchasing an asset, that decision will influence how much you have to spend in terms of maintaining it. Amount of money you put into maintenance will determine how long the asset is going to last, and so on and so forth. And the final thing, everything has to have a line of sight. You don't do anything to an asset unless it helps you achieve the organizational goals and objectives. Yeah, you don't just maintain the asset just because you like to maintain it. You need to make sure that it looks nice and so on. Well, you might need to make sure that it looks nice as long as it helps you achieve the organizational objectives. Yeah. So that kind of sets the scene. And in this context, we have this big buzzword. Everyone's talking about digital twins. So I can't have a talk really that doesn't actually have the term digital twins in it. In simple terms, a digital twin is a digital replica of a physical entity or a process, but there are lots of definitions. If you read 10 papers, you'll see 10 definitions. But these are some, so the one at the top, I find it useful because it's one of the earliest definitions of digital twins. But it's quite complicated. It says digital twin is an integrated multi-physics, multi-scale model, and so on. And especially because it was coined by NASA, it talks about a flying twin, and so on. But what I find often useful is to differentiate between digital twins and models. It's a question that people always ask me. We've been building models of systems for quite a long time. Now we have got this new term, digital twins. What's the real difference between a twin and say, for example, a simulation model that we all have? And this definition by the Center for Digital Build Britain kind of helps clarify that. It says a digital twin is different from a digital model because a digital twin has a connection to a physical counterpart. It's not a generic model of a type of machine. It's actually connected to a physical counterpart. And more importantly, there is a feedback loop as well. So using this digital twin, you can make decisions about that physical twin and then feed that back into that physical twin as well. So you can act on things. So what should these digital twins do? Now, you can see that the way I've phrased the question, I've done it quite carefully. I didn't say what can digital twins do. I said what should digital twins do, right? Because when I listen to a lot of talks, a lot of people talk about digital twins as if it's something that you can go to a supermarket and buy it and say, digital twins can do this, digital twins can do that, and so on. In my opinion, a digital twin can do whatever you design the digital twin to do. And you have to really think about what should it do and design a twin that helps you achieve those goals. And when you think about digital twins, I often think about two main questions. There are lots of questions, of course, but two main questions. What should the digital twin be of? And what should the digital twin do, help you do? These are the two questions that you have to think about. It could be a digital twin of a machine. It could be a digital twin of an entire system. It could be a digital twin of a fleet, and so on. So that question of is really, really important. And then what does it do? Because a digital twin can't do everything. It can do things that you design it to do. So let's look at this example. We work very closely with Siemens gas turbines, so I've used that as an example. So we have a real gas turbine working in some power plant somewhere, generating power, supporting a factory or a offshore a rig, and so on. What we have here, it's that digital twin. Okay. Now, this digital twin, as you can see, it's a three-dimensional model. And some people call a 3D model a digital twin as well. Okay, so this is where definitions are really important. So that 3D model allows you to really visualize what that digital twin looks like, right? But that's not enough. If we want to actually use the digital twin for actual decision making and control and so on. So what our physical assets often have is a number of sensors that allows you to capture data about the operational performance of the asset, the condition of the asset, and so on. So this particular gas turbine or the digital twin is actually saying it is providing some charts about some sensor data. It's saying that this particular machine is on at the moment. It is generating X amount of power, and it has been operating for 934 hours. So this is not a general model. It is about a specific asset that is operating at a particular site. So essentially, this digital twin allows us to see what is happening with our physical asset. So with all this data that we are able to collect from the physical asset into our digital twin, we should be able to learn something, right? And we heard a lot of things yesterday about how we can use data through machine learning, AI, and so on to understand anomalies, detect anomalies, predict failures, and so on. So for instance, for using that data, we should be able to learn what does normal look like. So this particular digital twin is now saying that it's the status is normal. Yeah. Now using this learning, our digital twin should be able to think and detect if something is going wrong, right? So this learning is good. So this is where we move from just machine learning into artificial intelligence. So you're moving from learning into thinking. Yeah. And so for doing that, in addition to machine learning models, you might need some physics-based models and so on embedded into the digital twin. So you're able to think and then say, oh, I detect some anomalies, detect some abnormal operation, and I'm predicting that this particular gas turbine is going to shut down in 7 ± 2 minutes. We talked about uncertainty yesterday. So nothing is certain, so ± 2 minutes. Yeah. So we are able to see, learn, and think. And the final, most important bit, act. If the digital twin should be able to then tell us, based on certain algorithms, optimization algorithms, and so on, what do we actually do about it? So in this case, saying reduce the load by 25%, so we can probably extend the life of the turbine, so we have enough time to get the spare parts in and get it fixed, not have a immediate shutdown. Yeah. Again, I'm not saying this is what a digital twin can do. This is what a digital twin should be able to do if you have appropriate data, models, algorithms built into the twin. Okay. Right. We heard a lot of challenges yesterday in different talks. Different speakers spoke about different challenges. So I'm not going to repeat all of those challenges. But when you think about complex systems and complex digital twins, some of the challenges that we have experienced, in addition to what the speakers yesterday have spoken about, merging asset behavior and operations and processes. So a lot of the ideas and the solutions that we see over and over again focus on a particular problem and focus typically on the assets themselves. But yesterday we also heard that just focusing on the assets is not enough. So we heard from Airbus, for example, when it comes to decision making, it's all about the operations, it's all about the performance, it's all about the costs and the risks involved. Is what do I do depends on what the impact of doing and not doing means, which means that in our digital twin ideas, we need to be able to merge both the assets as well as the operations and the processes that the assets are part of. So that merging of the assets and the operations and process is a major challenge. Second comes data integration. I think we spoke about this yesterday as well. A lot of different systems, especially when you're talking about the assets as well as the processes and so on. We might be getting some data from the sensors in the assets. We might be getting some data from the SCADA systems in the production plant. We might be getting some 3D model data about the building that the factory is and so on. So all of these different data sets will come with their own data standards, their own data formats, their own semantics, and so on. And when you're trying to bring all this data together into a digital twin to support your decision making, that brings a challenge to it. Third one, incremental development. And this is really important, and we need to really carefully think about this. When you're building digital twins of a complex system like a factory or a hospital or a rail network, for example, or an aircraft, we are not going to be building a digital twin of the entire aircraft on day one, right? You will identify specific problems that you want to address within the aircraft. We want to pick the low-hanging fruit, for example. So we might be building a digital twin of the engine or a component within the engine. We might be building a digital twin then about the of the landing gear, or even the component of the critical component of a landing gear, and so on. And gradually and incrementally, you will build up into the digital twin of an aircraft. And probably we don't yet have a digital twin of a complete aircraft, right? We might have digital twins of individual components and say, okay, when you put all of these together, we have the digital twin of the aircraft. But in my mind, the real power of the idea or the concept of a digital twin lies when you actually can combine different things together, not just individual things in isolation. So a digital twin of a landing gear and digital twin of an engine and digital twin of a wing, they all can provide you individual benefits, but you have to think about what you can do with them all together. Can the digital twin of a wing inform something about the maintenance of the landing gear? Maybe, maybe not. But it gives you that opportunity when all these twins are put together into a single concept. It allows you to bring these ideas together. And that's the last point, really, complex systems as system of systems. How do we start thinking about digital twins as a system of systems and a digitalized version of the system of systems? So those are the main challenges. I'm not claiming that I'm addressing all these challenges and so on, but I'll take you through some of the work that we have been doing. So on the idea of merging operations and assets, this is an example of a work that we have done several years ago with Rolls-Royce, looking at reliability of engines, specific components of engines, not the entire engine, of course. Now, one of the key things we try to do in this project is to look at how we can define reliability as not a univariate kind of function. Typically, reliability is defined as reliability as a function of time, reliability as a function of usage, and so on. Typically, single univariate systems. But in a typical aircraft, some of the components, the reliability of some of the components might be dependent both on the number of flying hours that the aircraft has taken, but also the number of landing and takeoff cycles as well. So you might see some components being dependent on these two variables, maybe multiple variables as well. So instead of thinking about a reliability curve, we thought about a reliability surface. You could be using copulas and so on. Well, what this allows us to do in this particular digital twin of a particular component of an engine, it allows us to do is it allows us to create a map with one axis being the number of landing and takeoff cycles, the other axis being the number of flying hours, and pinpoint where the aircraft is on that map. And once you can pinpoint where the aircraft is on that map, you might say, okay, this particular aircraft is very close to the number of landing and takeoff cycles in terms of its remaining useful life, but actually it's quite far away in terms of the number of flying hours in terms of its remaining useful life. So can we actually put that aircraft or that engine on a bit of a longer route so we can actually make more use of the remaining useful life than otherwise, and vice versa as well. So this is a kind of indication of how you might be able to merge the idea of maintenance and or condition of the asset with the operations that the asset is actually going into. So it's not just about optimizing maintenance, it's about a combination of operations and maintenance that we are thinking together. So it again links back to the idea of asset management. And then the graph on the right hand side, the charts on the right hand side, it looks at how if you are bringing an aircraft into the to the hangar for doing some maintenance on a particular component, can we use that opportunity to maintain other components based on their remaining useful life and the costs and risks involved? And that's not something new. Opportunistic maintenance is something that we all do in our plants. So it's bringing that idea together to get maximum value from that particular activity we have planned. I won't delve deep into this. Another project, we worked with Felixstowe Ports. Again, the key message here is, so the project was about maintenance, predictive maintenance of cranes. Unfortunately, as soon as the project started, it was in 2019. Right. So you know what happened. So everything shut down. So we couldn't actually do everything that we wanted to do. We were planning to actually do prognostics on some of the critical components on these key cranes, which are used to load and unload containers of the ships. What we ended up doing is more anomaly detection, because we weren't able to collect enough data that had failures. So we saw this problem yesterday as well, right? So we ended up doing anomaly detection. But the idea here, when we started the project, was to then link that to the crane operations, not just look at one crane, but as a fleet of cranes, and determine what the optimal maintenance plan across the fleet of cranes should be. Because when you went for the port operator, one crane is not useful. Right? It's that fleet of trains that allows them to operate as a port. And they might have 25, 30 cranes, out of which they will need at least 20 available at any point in time. So it's that concept of service availability that is becoming really, really important when it comes to fleet management. And we were lucky enough to be able to work with a train company later on to progress some of those ideas about fleet maintenance. So this is an example of a work that we did with Talgo. And we actually started the discussions with Pierre at Alstom as well. And some of the work that we have done, the foundation was actually built on some of the work that Pierre had done and published as well. So what we were doing here is looking at how we can actually merge predictive maintenance and planned maintenance together. Because ultimately, when you think about maintenance and the evolution of maintenance over time, people say, okay, we started off with reactive maintenance, and then we moved on to preventive maintenance, and now we are moving into predictive maintenance. But in terms of the thought process, when we moved from reactive to preventive, we moved from reactive to actually planned, right? Now, with predictive maintenance coming on board, if we start reacting to these alerts and alarms that our algorithms are saying, we are actually taking a step back into being reactive, right? So the idea should be, how do we use predictive maintenance technologies to help us plan? And when it comes to these fleets of assets like trains, cranes, aircraft, and so on, it's important to also understand that you already have a planned maintenance activity. There's already a schedule that you have built in, which you've organized based on the operations that the aircraft or the trains have to ply on. And as far as possible, we should not disrupt that plan. So this particular activity looked at how we can look at these predictive maintenance technologies, do prognostics, but then when we get these remaining useful lives predictions from these algorithms, how do we use that to merge that into the best fit into the existing PM schedules? So this work allowed us to reduce the disruptions in the fleet activity. So this algorithm that we developed, it produces a calendar like this that you can see, where the algorithm tells you when the train should be sent for operation, when the train should be sent for predictive maintenance, when the train should be sent for preventive maintenance, and so on. Right. So what it does is, if you see that particular component is close to its remaining useful life, it actually says, okay, don't operate this train on this particular day. So you can extend the remaining useful life a bit further, so you can actually slot that maintenance into the next PM slot. I'll skip the next couple of slides, which talks about integration of data and so on. So this is looking at the challenge of how we can actually develop these incremental twins and through a modular architecture. And the previous one talked about how we can actually bring different data models together using federated twins. Just to kind of wrap up my talk, the idea of a digital twin should be actually stretched a bit further. So it's not just about these four activities: see, learn, think, act. It's also we should try and build digital twins that allows assets to communicate with each other, cooperate with each other, and achieve a system goal. Something kind of similar to what we heard about the agentic kind of ideas yesterday. And we have done some work implementing these ideas so here we have a couple of assets or a fleet of assets that are actually collaborating with each other to improve its prognostics performance. Because as you know, some assets you don't have enough data, other assets we have a lot of data. So why can't the assets that have less data share or collaborate with the assets that have got more experience in data to improve its prediction performance? But the challenge here is to always which assets should we actually learn from. If you learn from some asset that is not actually in the same kind of environment that you're operating in, you might be doing the wrong kind of learning. So we use kind of hierarchical clustering techniques to understand which assets are actually behaving similar, so they can actually form this friendship group and start sharing data and models with each other and improve its prediction performance. Prediction is not the only thing that assets can do collaboratively. It can also plan production collaboratively as well. So this is an example where two assets that are able to do the same task is able to coordinate between themselves based on their health, in their condition. Say, okay, if I'm feeling bad, if I'm in a poor condition, you take more load than me. And when I'm maintained, then I'll take more load than you. Right. So, and this through the idea of agent-based systems, these assets can coordinate between each other and determine what is best for system optimality. And there's another example working with Boeing, where assets are actually coming together as communities to negotiate with suppliers to get the best kind of deal. So if one landing gear is saying, okay, I need to be replaced soon, how can a collection of landing gears come together and say, okay, we don't need to be maintained now, but if we come together as a group, we can get a better deal from the suppliers. Ultimately, we need to be able to do things like, so here in a mine, conveyor is saying that, okay, based on my prognostics, I'm expecting a failure soon. But then the crusher, which is crushing rocks and putting it onto the conveyor, is saying, okay, if I slow down a bit, it might help you out. It will increase your remaining useful life. So this is not a particular asset just determining its own destiny. It's another asset determining another asset's destiny. We are not there yet. We need to know, we need to develop models and algorithms and techniques where machines can understand not only its own behavior, but also how its actions affect other assets in the system. And that's where we need to get to ultimately. There's the idea of holistic digital twins, where the digital twins are learning system relationships and causalities and can adapt to different situations and ultimately deal with uncertainty. So I'll stop my talk here. Thank you.